So let's do a video then on the data table and the results and how we analyze the results. So this is a summary table for the range, R for range, and the time of flight data for the 45-degree projected ball bearing. And if you look over here, we have the mass. The mass is in grams, so this here will need to be divided by 1,000 later on when we do calculations. And when we do that, I'll bring it up. Angle was at 45 degrees. The measured height of Y was 1.55 meters. Now, if you remember, we actually had the board, and on the board was attached the pipe. And just to make it really clear, that pipe, when we drop the ball bearing from this height here, the height is actually the height from the bottom of the tube, the exit point of the tube, and where the ball bearing was released from the bottom of at the top there, which is that there becomes a change in height. And the reason why is because as this ball bearing is traveling down this tube up until this very last point, so let's draw that a little bit closer, up until this last point here, that ball, or the ball bearing, is actually being pulled down by gravity, and it's also got inertia in another direction as well that's being impeded by the tube that it's sitting in. As soon as that ball bearing leaves that tube, the tube is no longer putting any force at all onto that ball bearing, and the only force we have acting now is gravity in a down direction. So the change in height must be from this point here, the point where it leaves, to the point where it enters the tube. That is Y. So let's go back over here. We have the measured height, which is 1.55 meters. We had the measured average displacement, 1.45 meters, and the average time that it was in the air was 0.51 seconds. So let's go and calculate then, I guess, first the potential energy. And whoops, let's go back over to here now. Get rid of the pen. Home. There we go. And so the gravitational potential energy, and I've got the formula here, is mgh. So mass is this column over here. Mass is 13.78. So I'm going to go up to the top here. I'm going to put the gravitational potential energy is equal to the mass. Open up a bracket, click on that cell. And remember I said I need to divide by 1,000 because I need to convert that over to kilograms from grams. So it's m times g. So we push star, shift 8, G is 9.81 times the change in height, which is this here. The change in height is m already, it's in meters already, and so we'll just hit enter. And we have 0.210. And I'm going to grab now, I'm going to go down to the bottom right hand corner, grab and drag that all the way down. I can change, I haven't got my screen big enough at the moment, but I can change a number of decimal places. If I go up to the home, and then there's a little about above here, there's a .000, etc., decrease decimals, or we can go and increase the decimals. And if I click increase decimals, it increases the number of decimal places. Or decreases the number of decimal places. I reckon that's probably about enough there. Now, EK is a kinetic energy of when that ball leaves the tube, and given 100% conversion of energy or transformation of energy from potential to kinetic, that should be exactly the same as that. Now, we know that that's not actually completely true because it's not a frictionless surface, but we're going to assume that it is. So I'm going to say that each of those ones there, the kinetic energies, is equal to the potential. Then we have the next column over here, where I've put the formula UR. UR is a resultant velocity. So we're going to actually have a velocity as that ball bearing exits out of the tube. Let me get a different colored pen. As that ball bearing exits out of the tube, it's going to have an initial velocity that I'm going to call UR. It also has then a UY component and a UX component. So UX, UY, and UR. So UR is a resultant velocity. And the UR, interestingly enough, if we go and have a look at the kinetic energy formula, let's see where we can do that. Let's maybe scroll down and do that sort of down the bottom a bit more. I've got a bit of clean space. So the kinetic energy formula, KE, equals half mv squared. And if we rearrange this formula, then I multiply, let's get a different color pen. If I multiply this side by 2, that's going to cancel out the half. So I need to multiply this side by 2 as well. So 2ke equals mv squared. I want to then divide this side here by m, and that's going to get rid of that, but I need to divide that by m. And let's rewrite that at the moment. So I have 2ke on m equals v squared. And I want to get rid of that squared, so I'm going to take the square root of this side. We'll get rid of that squared there. I need to square root this side here. So I'm going to end up with v equals the square root of 2 times the kinetic energy over the mass. And that's a formula then that I've put up the top here, where I've got UR, that's this initial velocity here, UR is equal to the square root of 2ke, or the kinetic energy, divided by m. So let me just rub that writing there out, and let's put that formula in. Let's see if I can do that. Okay, so we're now going to say that the square root, so it's equal to the square root. And square root, it's SQRT. And just notice that it comes up, the square root of, and it comes up with a bracket, so it's going to be 2 multiplied by the kinetic energy, which is this one here. All right, and I'm going to divide that by m, which is that, divided by 1000. So we need to put a few more brackets in here. So it's divided by that. And I'm going to put another bracket in here because it's the square root of all of those things. So it's the square root of all of this that happens in here, which is 2 times the kinetic energy, divided by the mass, which is y5 over 1000. Let me get rid of that last one on the end there and turn it around. And with any luck, that'll give us the kinetic energy, the velocity of that object. I'm going to drag that formula there down, and I'm going to go back and reduce the number of decimal places like I was talking about before. All right, so this part becomes a little bit tricky because Excel is a little bit funny. I'll just bring this window here over and see if we can maybe scroll across. Not sure that we can. What it says, try that again. No, it's not going to want to play. Okay, basically what it says is that the cos function, or any of the trigonometric functions in Excel, they expect the value that you're going to put into the equation to be in radians, not in degrees. So we want to work out, we've got here an angle of 45 degrees. We need to convert that over to radians when we use our formula over here. And let me see if I can bring this over again. Let me try once more. And it's going to scroll. Is it funny? No, okay. So the cos function expects radians to supply an angle to cos in degrees, multiply the angle by pi over 180, or use a radians function to convert to radians. For example, to get the cos of 60 degrees, you can use either of the formulas below. I like this one here, where it's got cos of the, where it's got cos radians, and this value here is going to be 45 in the example that we've just been using. So if I go back up into here, and I'm going to say then that this is equal to, let me paste that in, so it's going to be equal to AF45. So if I get rid of that, remember to calculate the UX component, I need to do the UR, the resultant velocity, AF5 multiplied by cos, we're converting to radians, Z5, Z5 being this column here, 45. So we're converting the 45 degrees to radians, and saying that get the cos of that and multiply it by the AF5, which is our resultant velocity over here. And we should come up with about 3.9, which is what it is when I worked it out on my calculator. Again, I'm going to drag that down. I'm going to reduce the number of decimal places a bit. So we've got about 3.9 meters per second. I didn't put the units up in here, and I should have. It's in meters per second. We do the same thing now for the sine of 45. So instead of being cos, I'm going to change that to sine, S-I-N, sin. AF45, so it's the 45 degree angle, multiplied by the sine in radians of Z5, which is up there. I'm going to hit enter. And there we go. And I guess it's interesting to note at this point that the values here are the same, 3.9 and 3.9. And that's the reason why that is because the cos of 45 is 0.707 and the sine of 45 is 0.707. They're equivalent values. And that's quite interesting because what that means is we've actually projected an object. So we've shot it out at an angle of 45 degrees. And that 45 degrees, at 45 degrees, you've got the velocity in the x direction is equivalent to velocity in the y direction. They are equivalent to each other. So the 45 degree angle is actually going to be the optimum angle for which a projectile should be shot out at. So let's just clear this up a little bit. We've got 2 pens. Erase all this stuff off here at the moment, make it a bit neater. And what we're going to look at next then, I guess, is the theoretical. So we're over here now, we're going to look at the theoretical time of flight. And the theoretical time of flight is 2 times the u, so v naught, or ur, the resultant velocity, which is this one here, that velocity there, multiplied by the sine of the angle, 45 degrees, divided by g. So we can put this in straight into Excel as a formula, if I can find my mouse. And let's go and say then it's equal to, open bracket, 2 multiplied by u. So we're going to click on here, 2 multiplied by, oops, we need to say equals 2 multiplied by ur, multiplied by sine, open bracket, radians, open bracket, of 45 degrees, close bracket, close bracket, close bracket, close bracket, yep, divided by g, divided by g, which is 9.81, close bracket. And that should now be our theoretical time of flight, 0.79 seconds. I'm going to change that back a little bit, bring it back to the decimal place back a little bit, 0.79. So we had a measurement of, what did we get for a time? 0.51, we got 0.79. We said that our accuracy, our precision was plus or minus about 0.2 seconds. We could put that in here where we say the accuracy is insert symbol, so plus or minus, insert 0.2 seconds, close, so plus or minus 0.2 seconds. Let me decrease the size of that because it's huge. All right, and so we're almost within that sort of margin of inaccuracy there. Again, I'm going to drag that, take it and drag it down. That's all of my theoretical times that it should be flying for. And the theoretical range, I've got here ux times t. That's actually incorrect as a formula. I'm going to paste a proper formula in here now. So it's u, the range is equal to u squared. Let me just make that a little bit bigger. So it's u squared superscript times sine of 2, not q. It should be 2 theta. So I'm going to insert the symbol again. You'll probably need to go through the symbols palette and actually find where the symbols are. 2 theta divided by g. So I'm going to put in here, it's equal to u squared, which is u, that one there, u squared, use a little top hat, squared, multiplied by the sine, again, it's got to be in radians. Let me just scroll across a little bit so you can see what I'm writing here. The sine in radians of, it's 45 degrees, close, close, divided by g, which is 9.81, close bracket, and I'll just put an open bracket over here. And that should work out then. The theoretical range is 2.19 meters. That's quite large. I'll check that formula soon and see what's going on. See